It's my great pleasure to introduce Judy Fan, who's our colloquium speaker. Judy is one of my favorite cognitive scientists, really of any age. I think she's definitely one of the leading, by any objective standard, leading of the younger generation, people who have just junior faculty, or I don't even know how junior you are, but she's been an assistant professor at Stanford for a couple of years. I think that's a good estimate, right? And she's by any means one of the rising or glowing superstars of our field. She's won a number of awards: the Glushko Dissertation Prize, the NSF Career Award. I think you won that, right? Okay. Real time talking tonight. But none of that really that's not the reason that we invited her. I think of Judy as one of the most creative researchers I know of any stage in any field, and I really mean that deeply. She has a background coming out of neuroscience, and in many ways is very much at home talking to all the sorts of people who inhabit this building, who record signals from brains and try to make sense of them computationally. She's done a lot of that. She's worked with colleagues of ours whose work we know well, like Dan Yeamans was one of her mentors, and she has studied vision. A lot of her background is in visual psychophysics and visual neuroscience and computational neuroscience. But if you look at her research, some of which you'll see today, and a lot of which you won't even see today, she's gone in many other directions, or let's just say one key direction, which is from some of the most basic processes of perception and the things that you can describe with nice, elegant computational models, to aspects of cognition that really are what make us human, both biologically and also culturally. And you're definitely going to see some of that here. And so that means she studied things like artistic expression or creative expression in visual and other media. She's very interested in narrative expression. She's really interested in education, learning, and teaching, and how we make sense of the world symbolically and through data and explanation. And she's really moved towards these much more complex cognitive processes that are really distinctively human, both biologically and culturally, and increasingly really of great import in our current era. But she hasn't given up any of the rigor, or I would say her taste for rigor. And I know from a lot of interactions with Judy that what keeps her up at night is the struggle and the challenge of how do you get at these really important, hard things with the kind of rigor and precision that many of us grew up valuing and being inspired by in, for example, visual neuroscience and computational neuroscience. And I can't say she's completely solved that problem, because it might take a while. But it's a really great challenge. It's one that inspires me, the way she works on it. And I hope that it's one that we can all learn from and be inspired by, and to see where she is and where she's going with this. So, Judy, please tell us.
Okay, wow. Okay, I wasn't totally prepared for that. That was incredibly kind, Josh. I'm really, thank you, and thank you all for being here. I can't actually express how wonderful today has been so far. I have a lot of affection and respect for this department and community and the kind of values, scientific and otherwise, embodied in the work that you all do here. And so it really is a treat to spend a few minutes telling you about some of the work that we've been doing. So we study cognitive tools. What are those? Okay, let's start with something as familiar and simple as the number line. I've been told not to move around as much because we're using this mic. Okay, I'm gonna try to do that. Nature didn't give us the number line. We invented it, okay? So as the Spanish architect Antoni Gaudí once put it, there are no straight lines or sharp corners in nature, but that didn't stop us, okay? We created them anyway, and we extended the number line, of course, a few hundred years ago to create rectangular coordinates, which turned out to be super useful. They were genuinely cutting-edge tools for thought, for driving new mathematical discoveries, when René Descartes and his contemporaries realized that you could link up algebraic expressions with geometric curves in order to solve all kinds of mathematical puzzles, including this one that has stumped the world for millennia. How many are familiar with this particular, the Delian problem, this riddle of the Oracle of Delos? It's the problem of how do you double the volume of a perfect cube. It's really, really difficult to do using the mathematical methods of that community and time. And here's the solution for that. And it'd be really hard to overstate the impact of this invention over the last 4 centuries. That technology converted all kinds of problems like these, where you might want to find the set of values that satisfies 2 equations, into essentially problems that relied on locating points of intersection between 2 curves. Now, imagine what happened next to that revolutionary tool. It became something that we could take for granted. It became so useful that it's become basically indispensable to the way every generation is educated. Virtually every mathematics curriculum on the planet introduces a combination of symbolic and graphical notation for representing and manipulating mathematical objects. And the question that we wrestle with is, how did we get here? And what is it about the human mind that makes that kind of continual innovation possible? There are lots of ways of approaching that question from many different disciplinary perspectives, including history, anthropology, economics. And I think that cognitive science also has a really important contribution to make here. And I think the story begins at least 30 to 80,000 years ago, when anatomically modern humans began to mark up their physical environments, essentially, including these cave walls here, iconically, repurposing objects and surfaces in their surroundings into carriers of meaning. We obviously didn't stop at cave walls. The story of human learning and discovery is deeply intertwined with the story of technologies for making the invisible visible. So here are just a few examples from the history of science, which I love. We've got Darwin's finches, and these illustrations produced by John Gould, the ornithologist that Darwin worked very closely with. Only when you see these cases side by side does the kind of morphological variation begin to really become salient and pop out. We have the telescope that Galileo used to observe the movement of the moons around Jupiter, the kind of resolution that he needed in order to question the orthodoxy when it came to how the solar system was organized. We have Ramon y Cajal's much celebrated drawings of the retina as seen under the microscope, showing us what different parts of that part of the nervous system were like and how they were hooked up to one another. And in the 20th century, we have Feynman diagrams, named after, of course, the physicist Richard Feynman, showing us subatomic particles winking in and out of existence, events that we literally could not and will never be able to observe directly with the naked eye. And more than any other species, we leverage this understanding, this expanding understanding of the world in order to, well, maybe to go back just one beat, is that like, I want to draw your attention to the variation on this slide. So notice that some of these images are quite detailed and faithful, if you will, to the way the visual world looks to us when we open our eyes. Let's take Darwin's finches at the top left, for example. Others are much more schematic, but what all of these examples share in common is they leverage what I've been calling visual abstraction to communicate what we see and know about the world in a format that highlights what is relevant to notice, okay? And then building on that, we leverage that expanding understanding of the natural world through the use of those tools for learning in order to create new things. So for example, our detailed understanding of physical mechanics allowed us to design and then build high precision timekeeping devices. And a lot of this technological progress has been driven by our ability to continually reformulate our understanding of the world in terms of those useful abstractions that make it possible to re-engineer the physical world according to our design. So translating biological insights into bioengineering, physical theory into advanced physical instrumentation, neuroscience into medical devices, and quantum mechanics into modern electronics. Okay, so this is, a sampling the kind of phenomena that I take a lot of inspiration from, and the question we continue to wrestle with is like, what about us makes all of that possible? This is a schematic that I've been using over the last few years to help me think about the key behavioral phenomena in play, and that'll also serve as a framework for embedding the different lines of work that I'll be sharing with you. So this is one way of illustrating the traditional mode in cognitive psychology, my home discipline, which focuses on how people process information supplied by the external world. Here's how that picture is enriched by the study of social cognition, which considers the behavior of multiple individuals at once and how they interact with each other. When those activities are used in the service of learning about the world and sharing that knowledge with others, they've been argued to share important similarities with formal science, even when pursued by non-experts in everyday contexts. So building on that tradition, and with the goal of understanding how humans made all those remarkable discoveries and inventions that I shared with you just a minute ago, I'd like to argue that there's still two critical ingredients missing from this picture. First is an account of cognitive tools or technologies, material objects that encode information intended to have an impact on our minds, how and what we think. Second, I'd like to argue that the time has come to embrace science's natural complement, engineering, how people leverage their understanding of the world, whether it's through direct experience or is socially mediated, to create new and useful things. Because without a serious consideration, the engineering half of this picture, I would venture to say that we'll never be able to explain how and why the world as we know it came to be. So at its core, if I had to state it really bluntly, research in my group aims to close this loop, okay, to develop psychological theories that explain how we go about discovering useful abstractions that explain how the world works, jointly with theories that explain how we then apply those abstractions to go make new things. And my plan today is to tell you about some of the work that we've done so far along two lines. In the first part, I'm going to share with you what I think we figured out about how people leverage visual abstraction to communicate semantic knowledge, using freehand drawing as a central case study there. Ordinarily, in the second part, I would then have told you about our work investigating how people learn and coordinate on procedural abstractions when building physical things, aligned with the engineering segment. But today, I wanted to try something new with you all. So I wanted to instead share with you some of our emerging work. So I'm really curious to hear what you think. Exploring the cognitive foundations of data visualization. Okay, in which people harness multiple information modalities, graphical elements, words, and numbers to engage in statistical reasoning. In other words, to learn from finite amounts of evidence about aspects of the world that might be difficult or impossible to learn through direct observation by a single individual. Okay, and I'm still happy to chat with folks about our work on physical assembly and physical reasoning, probably at the reception, okay? So to dive into part one, how do we begin to think about how people use visual abstraction to communicate what they know and what they see? Here, I think it's useful to think about three behaviors that build successively on one another. So first, of course, visual perception, the problem of how we transform raw sensory inputs into semantically meaningful perceptual experiences. That in turn makes it possible to even contemplate visual production, okay, that ability to generate a set of markings that leave a meaningful and visible trace in the physical environment. And those come together during visual communication. How we decide just how to arrange those graphical elements and in what order in order to have a particular kind of impact on other minds, whether it is to inform or teach, persuade, collaborate, or any other purpose that we can put those marks to. Okay, so this is going to be an overview of the three studies that I'll be walking through. First, we'll begin with the question of what is the perceptual basis for understanding what a certain class, a subclass of pictures represents. So to get off the ground, we started by considering maybe the most concrete and familiar instantiation of visual abstraction, creating a drawing by hand that looks like something in the world. What makes it so easy to tell that the drawing on the left of this slide is meant to correspond to the realistic bird rendering on the right? There have been a lot of different ways of responding to that question. the two have been really dominant. So the first view is that we essentially see drawings as meaningful in representing things because drawings simply resemble objects in the world. Okay, like this drawing literally looks like the bird, and that's how we know. The second response is that drawings denote objects primarily as a matter of convention, and we only learn which drawings go with which objects and meanings from other people. So if you take this Chinese character, for example. So in an earlier line of work, my collaborators, close collaborators, Dan Yeamans, and my PhD advisor, Nick Turk-Brown, and I discovered that general purpose vision algorithms, so in this case, neural networks that compose multiple layers of learnable spatial convolutions that were trained on natural photographs, were capable of generalizing fairly strongly to even quite sparse sketches that didn't look photorealistic per se, suggesting that the problem of pictorial meaning and resemblance might be resolved simply by building better models of the ventral stream of visual processing, especially ones that accurately capture those operations performed in those brain regions. We were not the only ones to discover this. There are easily thousands of computer vision papers indexed by Google Scholar that use some kind of ConvNet or other neural network-based backbone to encode sketches and natural images for a variety of applications. All of those results you can kind of think of as vindicating an updated, modern resemblance-based account. It was also a really useful insight for us locally with other practical consequences. So in some more recent work led by Charles Liu, a former master's student in the lab, and in collaboration with Xiaolong Wang at UCSD, we built on top of those early findings to further stress test that resemblance account, basically taking a ConvNet backbone and then training a decoder on top that could map local elements in a sketch to corresponding elements in a photograph under the constraint that you could warp or rumple the sketch but not tear any holes in it, okay? And the success of that approach, I'm just demoing here, it's not really a result, it's like more of a demo. The success of that approach suggests that fairly strong spatial constraints govern how the parts of sketches correspond to the parts of real objects that they're meant to represent. Okay, so that's great, okay? We've got good enough trainable models of sketch understanding to build downstream applications that work pretty well, okay? I guess we can pack up and go home. But of course, that's not the whole story, okay? A static, deterministic account of visual processing falls short of explaining how we generate and make sense of drawings like these, which you might find all around this building. What these blobs and boxes, squiggles, and arrows mean depends on what we're talking about. So our next goal was to figure out how to incorporate that information about context to begin to account for a greater variety of graphical representations that we in fact use to communicate, ranging from more faithful pictures like those on the left here to the more obvious symbolic tokens on the right. Our first paper tackling that issue asked how people knew when they needed to produce a more faithful drawing and when they could get away with something more schematic or abstract. So in that study, we paired two people up to play a drawing game. The sketcher saw a display that looked something like this, where their goal was to draw the highlighted target object, okay, the third one here, and we varied what the other objects in the display were. On close trials, the distractors all belonged to the same basic level category, whereas on far trials, the distractors were from different categories, okay? Using this really simple manipulation, we discovered how readily ordinary folks, okay, can adjust the way that they use depiction to communicate, making more detailed and faithful drawings on those close trials when they needed their drawing to uniquely identify a particular exemplar, but then sparser drawings on the far trials when they could get away with these like category level abstractions. So here are some examples of actual drawings that we collected in that study. And we found that sketchers used fewer strokes on far trials, less ink, less time to produce those drawings, while still achieving ceiling accuracy on the fundamental task of communicating the identity of the target visual concept to the viewer, who themselves took less time on those trials to make their decisions. Then to capture that behavioral pattern, we proposed a computational model of the sketcher that consisted of two parts, okay? So a convnet to encode visual inputs into a generically abstract feature space, and then a second probabilistic decision-making module that inferred what kind of drawing to make depending on the context. I'm just going to give you the take-home from that study because I'm really excited to get to other work in this talk. So the take-home from our model ablation experiments was that both the capacity for visual abstraction, which you operationalize as the network layer in the visual encoder module, and sensitivity to context were critical for capturing how people manage to communicate about these objects at the appropriate level of abstraction. Okay, and then in more recent work, we pushed that idea even further to understand not only the impact of the current referential context on how people communicate, but also the conditions under which new graphical conventions might emerge. When memory for previous interactions with the same person leads people to produce even more abstract, maybe even proto-symbolic tokens over time whose meaning depends even more strongly on that shared history. Okay, so all of that was really exciting progress to me, but of course, people possess much richer knowledge about the world than just what things are called or what they look like. In a particularly important way that we use visual abstraction, especially in science, is to transmit mechanistic knowledge about how things work. So what is going on in people's minds when they make that move? Going beyond what is visually salient, let's say about a specific bird, to highlight underlying physical mechanisms. For example, how birds achieve flight in general. So you can imagine my excitement when Holly Huey, a wonderful former PhD student in the lab who's now at Adobe Research, was also fascinated by this question. And while we knew from very cool work by Frank Kyle and colleagues that people privilege mechanistic explanations when learning from others, and from work by Robert Tversky, Mickey Chi, Tanya Lombroso, and others that people can learn by producing explanations, we realized there was a lot that we didn't know about how people thought about visual explanations. Like, what do people think is supposed to go into a diagram that illustrates how something works, and what makes those different from an ordinary illustration that is just intended to look like something? One possibility that I'll sketch, which I'll call the cumulative hypothesis, is that people basically think of visual explanations as being like extended, augmented versions of ordinary depictions. So in this table, explanations would have all the things that depictions have to communicate visual appearance, and then tack on information about physical mechanism. Okay? An alternative possibility, which I'll call the dissociable hypothesis, is that people think of explanations as being images that pick out mechanistic abstractions while greatly de-emphasizing visual appearance. Okay, there's a kind of selectivity there. So to tease apart those possibilities, Holly designed a study to probe this question in two ways. First, by characterizing the content of visual explanations in detail and comparing them to visual depictions. And second, to measure how well either of those kinds of images actually help downstream viewers perform the task, extract the information that they really needed, whether it's about appearance or about mechanism. So rather than a lesson on bird flight, which is fascinating but complicated, Holly constructed 6 novel contraptions with a clearly observable mechanism for closing a circuit and turning on a light. Okay? So here's an example of one of those machines and the instructional video that participants watched. Okay? All right, participants in the study actually saw that twice, those 2 demonstrations twice, but there you go. So notice that this machine consists of 3 different kinds of parts, okay? There are causal parts that need to rotate to turn the light on. There are non-causal parts that look very similar, but don't actually cause the light to turn on. And then background structural elements that are colorful and hoist up the other parts are really important, but don't directly participate in the light activation circuit. Every participant produced explanations of some machines and depictions of other ones. On explanation trials, they were asked to imagine that their drawing would be used by someone else to understand how the object worked. And then on the depiction trials, they were asked to imagine that their drawing would be used by someone else to identify which object it was out of a lineup of similar looking objects. Okay, that's the manipulation, really simple. Using that procedure, we collected a large number of depictions and explanations of each of these 6 machines. Eyeballing them, the drawings seem to look different, okay? For example, maybe there's a little bit more background in the depictions. Maybe there's some more arrows in the explanations. But Holly wanted to be really systematic about this, so she crowdsourced tags assigning every single stroke in every drawing to one of 4 categories, okay? So one for each of the 3 kinds of physical parts, background, causal, and non-causal. And then a 4th category that was a catch-all for symbols, okay? So in this particular context, we're talking about arrows and motion lines. And then use those tags to compare what balance of semantic information people emphasize in these 2 conditions. What she found was that while people drew causal and non-causal parts in both conditions, they allocated more strokes to the causal part and explanations than the non-causal ones, okay? They also emphasize the background a bit more in depictions than explanations. And as we suspected, spent more of their ink on symbolic displays of motion and parts interacting in explanations than depictions. Okay, so already these results are incompatible with a strong version of the cumulative hypothesis, which would have predicted the relative emphasis on background causal and non-causal parts would be maintained even in the presence of arrows. But however reliable, those differences might just amount to stylistic variation that doesn't have any impact on how useful they are for the tasks that they are intended to support. So to measure those functional consequences of those decisions, Holly designed 3 different inference tasks. The first asked how easily you could tell what kind of action would be needed to operate the machine. So here, pull, rotate, or push. What you might expect a good mechanistic explanation to make clear. The second was to measure how well each drawing could be used for object identification, exactly what depictions are supposed to do. And then the third was a more challenging visual discrimination task where you had to determine which of 2 highlighted parts was the causal one, okay? Requiring you to establish a detailed mapping between the parts of the drawing to parts of the actual machine, something that you'd really only expect from a mechanistic explanation that also preserved enough information about the overall appearance and organization of the parts of the machine. So, under the cumulative hypothesis, what we should see is that explanations are at least as good as depictions for all tasks, but under the dissociable hypothesis that they might be better for the action task, but worse for the object task. And what Holly found was more consistent with the dissociable account, where explanations better communicated how the mechanism worked, but depictions were better for communicating object identity. Interestingly, explanations were not better in this sample for conveying the identity of the causal part in that challenging 3rd task, consistent with the idea that by leaving out a lot of the background details in some of those explanations, that they may have abstracted away the very information that would make it easier to link up specific parts of the drawing with parts of the machine. And the bottom line from those studies is that people share intuitions about what is supposed to go into a visual explanation, even if this is the first time they've been asked to generate one. And it can mean sacrificing visual fidelity to emphasize more abstract mechanistic information. And more generally, this work shows how important communicative context and goals are for understanding why people draw the way they do, why depictions look the way they do, and provided some experimental and analytic tools for characterizing the strategies people use to communicate visual information that is goal and context relevant. Okay, and then in this next section, we'll be asking, what would it take to develop artificial systems that are capable of human-like visual abstraction? And here's why. We fundamentally want useful scientific models of visual communication. And the work I've presented so far is representative of where we've prioritized making investments, namely the development of experimental paradigms and data sets to measure and characterize those behaviors in fuller ways across a broader range of settings. Meanwhile, we've also been investing considerable energy in evaluating how well any member of the steadily advancing cohort of machine learning systems might continue to be relevant and promising candidates for capturing more detailed patterns of human behavior in these high-dimensional tasks, specifically as models of human image understanding, as well as models of image creation. Okay, so the task setting that we consider takes inspiration from this famous series of drawings by Pablo Picasso. Some of these are very detailed. The last few are very, very abstract, yet all unmistakably bulls. Any scientific model of human visual abstraction worth its salt ought to be able to represent the ways in which these bulls are all different from one another, and somehow at the same time, all bullish to their core, right? Or rather, as bullish as they actually look to real human observers. So in this work, that was a huge team effort led by Kushan Mukherjee, who is defending this Friday before joining the lab as a postdoc, with contributions again from Holly, as well as Charles Liu, Yael Vinker, who's here actually, and Ryo Agina Kang. We began from the premise that like a strong test of whether we're on the right track towards those scientific models is that we'll be able to build algorithms that can generate and understand abstract images the way that people do. Sketch understanding, okay, is one of these deceptively simple yet poses a fundamental challenge for general purpose vision algorithms because, for one, it requires robustness to variation in sparsity, okay? Like some sketches are more detailed than others, you could say. And two, because sketches demand tolerance for semantic ambiguity, because sketches can reliably evoke multiple meanings. So we created a benchmark, which we call SEVA, to pose those challenges explicitly. Okay, so we collected 90,000 hand-drawn sketches made by about 5,500 people of 128 visual concepts under varying production budgets. So here's some examples of what it looks like when people had to create sketches cued by a photo. These are photos taken from the Things data set, if you're familiar with that, in less and less time. Okay, so by the time we get to the 4 seconds, they're real sketchy. We then took those drawings and then showed them to both people and 17 different then state-of-the-art vision algorithms representing a broad array of different kind of architectural commitments and strategies and training protocols. Yes?
Quick question of clarification. Do people get to think about it before you start the timer, or did they see it and then they have 4 seconds?
That's something that's been haunting me for 2 years. Not enough. I think they should, no. And I think, so what we're studying.
That time include both thinking and drawing.
Thinking and drawing. So they see the image and then they have to go. Okay, so we don't know exactly how, there is this restriction on the overall trial duration. I think that to really get at the bull phenomenon, I would want to give them unlimited planning time and then just limited execution time, and that would have been the way to do it. This is not that, okay? So there's like another data set that has yet to be born that isolates that more directly. Okay, yes. So the 4-second drawings are like quite derpy. Okay, that's like the technical term of art for that. But they are like what people did in those settings, okay? So we had all of these different sketches. They look the way they look under those conditions. Then both people and those vision algorithms perform the same sketch categorization task, allowing us to measure the full distribution of labels evoked by every individual sketch. Okay. The first thing we established was that as you give people more time to think about how to make and then go and make a detailed sketch, those sketches get more recognizable to models and people. They're less ambiguous as measured by the entropy of the label distribution. And even when the guess is wrong, okay, not the top one, okay, it's more likely to at least be in the right semantic neighborhood estimated by language embeddings. So that's reassuring. But then we dug in a little bit deeper and then found that while some models do, honest to goodness, perform better the recognition task than other models, the variation across models in terms of performance is totally dwarfed by the gap between models and people. The reliable signal in human recognition in terms of both performance, which I'm showing on the left, and also relative uncertainty about the meaning of a sketch. Okay? So that suggests there's still a sizable human model gap in alignment to close here in terms of for sketch understanding. Nevertheless, okay, at the time we conducted this benchmark, we noticed that the CLIP-trained models were outperforming the others, making it a reasonable candidate to begin to explore generative models of sketch production built on top. So we explored the capabilities of a particularly cool sketch generation algorithm named Clipasso, whose development was led by Yael Vinker. We asked Clipasso to generate some sketches as well, and also manipulated its production budget. And in this case, the unit now, the currency, is the number of strokes, which is different, which I know, okay? And what we found is that even while human drawings and Clipasso's drawings were similarly recognizable, okay, across the 4 production budgets. By the way, this overlap in recognition and recognizability is like totally coincidental, given how the units are totally different. But we found that the really intriguing discovery here is that humans in Clipasso sparsify their drawings differently. So what I'm plotting on the y-axis on the right-hand side here is the divergence between the label distributions assigned by people to sketches produced by other people and sketches produced by Clipasso under those different budgets. So in other words, if you take seriously like a functional view of sketches as being for communicating concepts and characterize their meaning in terms of the full distribution of the labels and meanings that it evokes, then even though the 32-stroke Clipasso drawings and the 32-second human sketches look different when you look at them, okay, stylistically they are different, they are also quite functionally similar in terms of like the set of meanings that they convey and the distribution of meanings they evoke. On the other hand, as you tighten the production budget, that's where you really start to see much larger divergences between people and Clipasso. And we're hoping that this SEVA benchmark will be a useful resource for others who are interested in developing models of human-like visual abstraction. Okay. Now, in the second, and I think shorter part, I'll give you a sneak preview of our newest and mostly unpublished work on multimodal abstractions and how they are used to support statistical reasoning. So back to that Cartesian coordinate plane. We're a room full of scientists. You don't need me to tell you when you're making observations about the world, it's never this clean. Instead of perfect lines, we might actually collect something like this, right? Collection of data points, they land where they land, and from which we try to infer some underlying structure with the actual generative process that gave rise to them. That inferential move is a fundamental building block of scientific reasoning, and we sure don't do it just by memorizing everything we've ever seen and thinking real hard. We use technologies, okay? Right? At the beginning of my talk, I showed you these examples of the use of drawings produced by hand as a particularly enduring and versatile, accessible tool for making the invisible visible. I think that's remarkable and worth understanding. But perhaps one of the most impactful technologies to have been developed in the modern era was the invention of data visualization. Like the telescope and microscope, plots help to resolve parts of the world that you can't see directly. But unlike either of those optical technologies, it allows you to see patterns and phenomena that might be too large, too noisy, too slow to see with our own eyes. They're ubiquitous in the news, the cornerstone of evidence-based decision-making in business and government, and they're indispensable in every field of science and engineering. What I'm showing you here is one of the first time series plots drawn ever by William Playfair in 1786 to show the balance of imports and exports from England over an 80-year period, from 1700 to 1780. For a while, imports exceeded exports, but But then the relationship flipped in the 1750s as exports really took off. Here's the thing. Unlike a drawing of one of Darwin's finches, okay, if you haven't seen one of these kinds of images before, it may not be obvious what you're looking at. But once you learn how, it's a kind of superpower, right? Like, so many individual observations can be distilled into a single graphic that tells a story that you can read just by looking. And that's not even all the reasons to care about plots. Because they're such a powerful tool for helping people update and calibrate their beliefs about a complicated world, developing the skills to read and interpret and even make graphs has long been a goal of STEM education in this country, something that's becoming even more important over time. The New York Times broke a story, this is actually from about a year ago now, about recovery from COVID-related learning loss in mathematics, based on work led by some of our education colleagues at Stanford and Harvard. And it looks like across a bunch of different states, the orange arrows are there, which means that there's been some recovery, but there's still a long way to go. And I think that successful theories that explain how people use these kinds of images to discover and communicate important quantitative insights will help us equip people with the kind of quantitative data literacy skills that they need more generally. So I'm going to highlight briefly 3 directions that we're pursuing in this vein. Our first question asks about the underlying operations that are needed to understand plots. So the strategy that we've been taking is to obtain machine learning systems that can handle questions about data visualizations at all, assess alignment with people, and then interrogate the source of any of those gaps, any gaps there might be, okay? What we need, of course, to get off the ground is some way of measuring understanding. So here's what that might look like. Say we're looking together at this stacked bar plot, and someone asks you about the cost of peanuts in Las Vegas, okay? You take a moment to take it all in, scan around. Suppose that person then gave you 4 options to choose from, okay? I added the little charcoal thing. Now, if you thought it was A, you would be right. But that's not what some prominent vision language models say, given this very same question. So in a Herculean benchmarking effort led by Arnav Verma, a current RA in the lab who's actually headed to the ECS program right here in the fall, we've conducted careful comparisons between humans and AI systems on 6 commonly used tests of graph-based reasoning, sourced from across the education, health, visualization, psychology, machine learning communities. All 6 of these tests were administered in as parallel a manner as possible to both human participants and several of these so-called multimodal AI systems, and that had been the ones that made it into this benchmark had been claimed displaying competence on other kinds of visually grounded reasoning tasks. We then recorded not only the overall score achieved by humans and these models, but the full set of error patterns they produced, which allowed us to assess, even when a model or a person got a question wrong, to see if they're getting things wrong in similar ways. What did we find? Here I'm going to show you for each of the 6 tests we included. They have funny names like GGR, VLAT, CALVI, HOLF multi, actually we made those. The bad name there is my fault. And also ChartQA, a subset from ChartQA. We recorded how well, we computed how well each of the models, so these are the ones that are showing up on XTIX in blue, orange, purple, and red, how well they did compared to how well humans did, that will show up in green. These were US adults who had taken at least one high school math class, okay? First, I want to give you a sense of how well these people did. That's our reference point here. This is how well all the models did. So we have, in this study, 2 variants of BLIP2 Flan T5, 3 variants of Lava-based models, specialized systems such as Matcha and its base model, Pixdestruct, and finally a closed proprietary model, GPT-4V. Across all these assessments, we did see a meaningful gap between models and humans, both under a more lenient and a more strict grading protocol. This is a gap that we might have missed had we relied exclusively on the chart understanding benchmarks that are currently most popular in the machine learning literature. So this is the reason why we included chart QA, which is the rightmost facet on this slide. Okay, where the gap seems a lot smaller. CALVI, which is the third one, is really interesting because these are adversarially designed plots that have like funny y-axis like limits that require you to really attend closely. So like that's one where we also see somewhat larger gaps. We also analyze their full error patterns, so which can be really telling when no one is quite at ceiling. Again, there's only one way to get all the questions right, but there are lots of ways that you can be wrong and wrong reliably. So we found that even though GPT-4V might look to be approaching human-level performance, none of these models, GPT-4V included, generated human-like error patterns. So this is shown by all the dots here, falling well below the green shaded area, which represents the human noise ceiling. So the upshot is that while currently developing VLMs remain exciting and promising testbeds for developing and parameterizing the hypothesis space of possible cognitive models of visualization understanding, there still are these systematic behavioral gaps that are worth interrogating further to realize those models' full potential. In parallel, we've also been developing experimental paradigms to probe a related facet of visualization understanding, the ability to select the appropriate plot to address your epistemic goal, okay? So I'm gonna talk to you about that next. The way we set up the problem is to imagine that there's some question that you have about a data set, right? Some, what I've been calling epistemic goal that a person is trying to satisfy, like, for example, like which group is better, okay? Let's say the left agent is trying to pick the plot to help shift the person's beliefs appropriately, okay? But if they had a different question in mind, maybe they might need a different plot, okay? That's the intuition. So this is a line of work that was launched by Holly Huey, and we formulated in a study hundreds of different questions that could, in principle, be answered by using real publicly available data sets. In this case, these are data sets that ship with base R. So here's an example of a scary one, tracking airplanes and bird strikes. Okay, what is the average speed of aircrafts flying in overcast skies that encounter bird strikes at 0 to 5K miles? We then presented participants with a menu.
Can I ask
Sure.
what is 5K miles?
Altitude. Yeah.
I'm sure it's not 5,000.
Sorry, 5.
Okay.
Hold on. That might be a typo on my part. I don't think the question
many
inherited
data
that.
sets have lots of typos.
What's the speed? What's the speed? 5,000. What's the speed?
Anyways, don't worry about it.
I'm starting to, but I'm going to resist that urge right now. No, I think that, yeah. So
But a lot, if this is the standard, they're full of all sorts of typos.
this is a templated thing. I think there are, basically, a lot of these questions are kind of funny, and I think they could have been smoothed over a bit more. So this is like, yeah, no, it's good. So, so we had all these questions. Some of them were like better put than others, but we presented participants with a menu of possible graphs that they might show someone else in order to help them answer that question, however they interpreted that question, okay? Whatever it is, those are the strings that we're showing to people, okay? And they could choose from this menu, either a bar plot, line plot, or scatter plot. Some of them were more distilled, some of them were more disaggregated, okay? And then we measured how often they picked each one in order to construct a choice distribution over plots, okay? So here's what it looked like on average for the retrieve value questions in our stimulus set. This is like one kind of task, and there are like other ones that'll like ask you to like compute some kind of difference between two values. This is the retrieve value subset of items. We then tested various hypothetical strategies that people might have used to pick the plots that they did. Clearly, they are showing some kind of bias here. It's a black curve. The purple curves here represent the predictions of like bar plot, line plot, or scatter plot purists. Okay, they just like always went for the bar plot, but just like didn't care whether they had 3 variables plotted or more. We also considered the possibility that people might prefer more targeted visualizations overall, but not really care about what type of graph they were sharing. Maybe they might prefer ones that show more of the data, maybe ones that hide, less of the variation in the data. The best candidate we found that we considered was the proposal that people are maybe actually sensitive to the features of those plots that were relevant for answering the question. And in fact, actually predicted the performance of about 1,700 other participants who tried answering every one of those questions, however weirdly put, when paired with every possible plot. Okay, so we went and actually measured performance, and then we constructed the distribution based on those performance levels, and then use that task in order to use the data from that task in order to generate predictions of the audience sensitive hypothesis. And this is where this is how the shape of those curves look when we're only considering the retrieved value items. But if you look at the data set as a whole, we found that this audience-sensitive proposal did well across the board. So what I'm showing here is essentially a model fit measure defined over the divergence between the predicted and the actual human choice distributions. Has a name, the Jensen-Shannon divergence, like an average of KL divergence, but both ways. So I'm excited about that result as an initial validation of a strategy for measuring visualization understanding using more open-ended tasks, and also because it suggests that even non-experts, you could say, people who might not be professional scientists, are sensitive to those features of plots that make some suitable for answering some questions than others. And honestly, as someone who teaches intro stats for a living, gives me hope. In the final leg of our journey, we're going to take another critical look at this problem of measurement, okay? So a few minutes ago, I showed you some results when using these 6 tests of data visualization understanding. These are the ones that we have today, which is why we use them in our benchmark study. Our question in this last study, in work that's actually now in press, and led by this extraordinary postdoc in our lab, Eric Brockbank, also with Arnav Verma, we're asking what are these tests actually measuring, and are they measuring the skills in the best possible way, and can we do better? Okay, so here are some initial steps towards answering those questions. To get some traction, we started with these 2, GGR and VLAT, these being some of the most widely used and established tests. We gave GGR and VLAT as a composite test to a large and diverse sample of US adults, actually 2 samples, one that was recruited on the UCSD campus, and another that was recruited over Prolific under the constraint that it had to be a demographically representative sample. And what I'm showing on the left is that we get pretty convergent estimates of the difficulty of individual items in both the college campus sample and the US representative sample, which I think is reassuring. On the right, what I'm showing is that people who did well on one test often did well on the other, suggesting that maybe the 2 tests are measuring some of the same things or similar things. And the question is what are those things? One possibility is that those 2 tests track how much easier some plots are to understand than others. If so, those plots should be reliably hard or easy across the board, like maybe bar plots are kind of easy, but stack area charts are more challenging. It seemed to us that clearly there's a lot more going on here. Performance wasn't consistent for a given kind, wasn't always consistent for a given kind of plot within or across tests, and there weren't even enough items to be able to establish a direct link between the type of graph and performance, because actually in each of these tests, there's generally 1 instance of each class of graph. So that also made it challenging. We also dug into the patterns of mistakes that people made and found that the best way to predict those patterns on these 2 tests wasn't the kind of plot or even the type of question, right? maybe find the max or identify clusters or characterize distribution or retrieve value, right? These are all common ways of describing the ontology of tasks involving plots. But it really seemed from this analysis that other underlying factors that aren't well described by the ontology are really accounting for error patterns much more efficiently. So here I'm showing you how much better a parsimonious 4-factor model does than one that uses the groupings that you might think of to use to organize the set of skills needed to understand any graph. Okay, so I'm not going to unpack everything on this slide, but this is just meant to illustrate that there seems to be something that is going on here that isn't obviously mappable to the ways that we talk about what the component skills are, and that you might actually see in textbooks or in instructional materials when it comes to how to break into data visualizations. And even if existing assessments might not be testing and characterizing visualization understanding in the best possible way, we're really trying to take that as a glass half full call to action to develop improved measures, so stay tuned for those. More generally, the reason I think this work establishing the perceptual and cognitive foundations of data visualization is so important is because it'll give us a chance to use what we learn to eventually help people, learners, in real educational settings, calibrate their understanding of a complicated and changing world that we can ever only observe a part of. And these kind of integrative efforts, if you will, that connect fundamental science to that wider world that we all inhabit, exemplify where we're going with all of this. We really want to develop psychological theories that explain how people use the suite of cognitive technologies that we've inherited and continue to innovate on. We want to understand why that toolkit looks the way it does, what future cognitive tools might work even better. In the long run, I think that understanding how these tools work and how to make them better like really matters, because it's like these tools that are the heart of two of our most impactful and generative activities. First, education, which is the institution and maybe more importantly, the expectation that every generation of human learners should be able to stand on the shoulders of the last and see further. And design, the suite of activities and habits of mind that help people continually reimagine how the world could be better and then go out and make it true. So with that, I want to thank all of the folks who've been involved in this work and other lines of work in the lab. It would not have been possible without an amazing research team and network of collaborators and colleagues in many different places, including here. So I want to thank all of them, all of you for your attention, and I'm happy to take questions if we have time, which we might not. Okay, great, thank you. I see hand. Okay.
Thank you so much for the talk. One thing I'm curious about is, so in a lot of your examples, specifically relating to depictions, there seems to be this kind of one-dimensional axis between things that are like more detailed and faithful or versus more sparse. But I'm kind of curious about cases where people actually diverge and produce things that are like actually false or like counterfactual. So I'm thinking like, if I'm drawing a glass of water, I want to indicate that it's full, I'll like shade it in blue, even though like in real life, glasses aren't like blue when they have water. And I feel like that depends a lot on culture and language and stuff like that. Like I, speak a language where water is described as blue. I like have been around pools, which are usually painted blue on the inside and so on. And that could sort of depend. So I'm just wondering how you thought about some of those cases.
Yeah. There's a large literature in philosophy in like the area of aesthetics that I take inspiration from that begins from a similar premise, which is like, how is it possible that we understand pictures that are false, right? Like pictures of like fictional individuals or unicorns or like glasses with like blue water, even if it doesn't look that way. The tack that we've been taking in our own empirical work is to not begin from that premise, right? Which is that rather than thinking of them as false, this is the actual data that people are generating under some objective, and we're trying to figure out what that is. Right? And so the reasons why they might render the water depicted in that depicted glass is for some reason, and we're interested in those stakes that you identified, to what degree it captures faithfully the visual appearance, the phenomenology of looking at a glass of water in a room where the glass is in front of you, as opposed to a kind of acquired convention for how you depict water, for example. I think those are like very reasonable sources of like constraints on why people make those representational decisions. So I think those are like the kind of questions. It's just rather than thinking of some drawings as good or bad, false or true, we just find it a lot more useful and productive to think of like, okay, these are the drawings people make under those conditions. Why? Why do they look that way and not another? If that helps. Thanks for your question.
Sure. Thank you very much. I am curious about, so I thought something you only very briefly touched on that is super potentially interesting is the human likeness of errors that artificial systems make in gravity and visualization. And I guess, in a way, actually, that seems especially useful for an artificial system because if I am producing a visualization, I know what people will understand it to be if they understand it correctly, but I don't know, I might have a lot of difficulty imagining how it would be misunderstood. And so that actually seems like a task which was literally like, how else might this be misunderstood? Understood would be a very, very valuable thing. And I want to ask, like, what is our state-of-the-art model of that? Of like how graphs are misunderstood, visualizations are misunderstood, and is it an interpretable state-of-the-art model from a scientific
Oh,
perspective?
gosh,
Does it
okay.
give us insights into
Yeah.
the workings of the actual inner workings,
Okay.
visualization, understanding?
It's really good question. So I'm going to engage with it, which is, so there's a phenomenon which, some of us in the room study, which is like perspective taking, which is hard, but doable in some contexts. It can be possible to imagine what the world must look like from the viewpoint of someone else, and there are various paradigms for studying that. It also seems like the capacity for doing that very quickly and accurately can change with practice. And so there's like a role for expertise and experience to play in like shaping your ability to do that. One way in which that manifests, I'm not going to refer to like the VLM results at all here, but just like to sketch the like shape of the problem. It's like teachers, like the kind of expertise, one of many kinds of expertise that teachers, really skilled teachers develop is the ability to notice it is called, misconceptions when they listen to learners describe how they're thinking about a problem, right? So it may be that the final response or answer that a student gives to a math problem is like wrong, but it's not only that it's wrong, like the relevant question isn't always that it's wrong or right, but rather what is the nature of the misconception or misperception, or what is the gap between the normatively correct way of representing the problem and proceeding through the different steps and whatever the student did. Okay, so one way in which I think, maybe I will just very, very briefly, if it's okay, speak to how we've been thinking about this question in the modern era of extremely large machine learning systems, is to interrogate the kind of operations and like conceptual primitives, so to speak, that these systems rely on when they get an answer right or wrong, using the suite of like tools that go under the banner of like mechanistic interpretability, but we could call cognitive systems neuroscience for artificial neural networks, in order to diagnose where right answers and wrong answers come from. And it'd be really, really nice. I'm not going to go into those in detail because of the but that's a kind of like strategy you might take to connect what is the operations that are being performed in these systems that do not immediately lend themselves to those kind of interpretations at the same time, and then connect those to what has been called like knowledge graphs, the underlying knowledge graph that a person might hold or not hold. Okay, so like that's like a like a way of setting up the problem, I think, and like sometimes the issue, the bottleneck might be perceptual as such. And other times it might be like a bottleneck, or the gap might have to do with like a reasoning step. And the goal is to really expose what those steps are, have tools for diagnosing them, so that in principle you could use them to diagnose those misconceptions or misperceptions, mistakes, missteps in anybody or any system. That's very, like, very, very hard, of course. But these like challenging problems are like I think like a tool that we can use in like towards that end. Okay, I hope some of that made sense. I've like a lot of thoughts
Can I
about.
ask a follow-up?
Yeah,
in
go
relation to this?
Yeah.
Like, so, I think it makes sense, but, so in particular, you helped us out here by highlighting
I
in
know.
gray that red, like the right part of the graph to pay attention to, right?
I
And one
did
of the
do that.
reasons why you might have trouble answering this question, I'm just trying to see if I understand.
Yeah.
Is that you might not know which part of the thing to pay attention to answer the question.
Yep.
Or you might know what part to pay attention to, but you
Yep.
might not know what to do with it. How
Yep.
do you take that
Yep.
red rectangle and kind of relate it to the information, the information on the y-axis? Or you might not know, even if you know how to do that, how to turn that into the answer to the question.
Yep.
Are those the kind of, that's the kind of.
Well, yeah, like those are the kind of teaching moves that like a human
Yeah, but
educator
it
might actually
seems
take.
like you could.
Yeah.
People have even tried to break this down, like some of Eric Schultz's group work, for example, where they say, like, you could ask the model or people,
Mm-hmm.
like, how big is the red rectangle in the second column?
Yep.
Something that doesn't require any reasoning, but just.
Yeah,
like,
yeah,
inspection.
yeah.
Or something, or like, which blue rectangle is the height, like something
Yeah.
like that, for example. Is that the
Yeah.
kind of thing you're doing?
Yeah. So we started with stimuli like these. So this is a very, very new work that's being led by, yes, exactly. So this is being led by Alexa Tartaglini, collaboration with Chris Potts, and we started with stimuli like these, like the real wild plots and questions, and then realized we wanted to drill down. So they're like both taking these plots and asking a variety of different questions, including these more basic ones, so to speak. Also, we've realized that like really stripping these down to much simpler versions of it that still contain the like core like multimodal integration challenge. Like even like we're like, currently like running these studies on like number line stimuli essentially to like understand how you might judge the distance between two data points on the number line. For example, but like there are like all these different routes to it because this is like this the point is that this is complicated, and so like decomposing it is like part of the
Right, but
challenge.
It could be like.
Yeah,
something
yeah.
that across how you teach these skills.
Yep.
Break them down into subskills.
Exactly,
and
yeah.
how you assess them in the human.
That's right. Yeah, right. So there's assessment, and then also like the reason why this black, like shaded, charcoal rectangle is there is because like there's some guess that I had about what might be a bottleneck to rapidly looking at the appropriate feature of the plot. Okay.
Could I follow up on that?
Yeah,
question?
sure. Okay, this is-
So,
yeah.
when I first looked at this plot, I thought it was actually ambiguous, and I wasn't sure whether the height of the bars all started at 0, and we're seeing one of them in front of another,
I know.
or
I know.
starting with the cheapest one.
like
or
dodge equals
not.
true, yeah.
But that's not my question.
Yeah.
My question is this: you've been focusing on for adults who've been exposed to like lots of different kinds of media. What are the best ways to present information so that people can get it and get it efficiently, so forth. But there's another question, which is, I think for when we first see a new kind of graph, like this might actually be the first time I ever saw one that stacked up. At least it's been a while since I've
That's
seen one
exciting.
that stacks up like this.
That's what they look like.
It's not so obvious when you first see it.
Yeah, it's
And
not.
as we get very used to seeing them, seeing things that are different can become really harder, right? So for example, event-related potentials where negative goes up drives me crazy.
Right?
Every time I see it.
Yeah,
You know,
right?
So I wonder, I mean, what do you think about the question of how these kinds of representations should be structured so that they're easy for kids to learn?
Yeah.
Right? That
Oh.
if you start out with none of these representations, what would you put into the earliest ones that you want kids to learn about?
Yeah.
And how would you progress from there?
Yeah, that's a very good question. Okay, yes, and actually there are like versions. I feel like there's a few minutes ago, Nancy and I were talking about something kind of related when it comes to like how, people break into this class of visual inputs at all, right? There's a sense in which you're building on top of a lot of like neurotypical ordinary visual and cognitive development in order to grasp the presence of different shapes in certain spatial arrangements. It relies on literacy as such, being able to. There are a bunch of like conceptual primitives and like more basic competencies that you might need to build up first. It might be that there is like a sequence of experiences that build from the. Like that's a really good question. I don't have answers to that curriculum design question, but I think it's a great question, and it feels like there are thoughts.
I was gonna say,
yeah.
Just to build on that, it seems like, the whole back third of the cortex does vision, and it's a spectacular set of machinery that extracts all these different rich kinds of visual representations, from orientations to heights to shapes to landscapes, all of which are possible spaces we can use, right? And so it seems like the essence of making a good graph is figuring out how to make a visualization that, taps into some of that machinery.
Yeah.
Especially if you build a map on
Like what makes visual scenes in general easier and more fluent to process, right? Things that aren't particularly cluttered, right? If you're interested in like the kind of problem of like visual search over those scenes, there are aspects of those processes that are co-opted in order to identify the appropriate sub-region of this image to look at, right? You might imagine like designing those initial graphs to cohere more with those kinds of scenes, right? And then there's like this step of like mapping the components of these scenes to concepts that you also need to learn about, and that can be really hard initially, and then become faster and faster and easier over time. And I think it's really fascinating what is happening as that takes place. Yes, and also, yes, but then also, what should I do?
And this is really cool. Why don't we wrap up and allow people who need to leave to go
Yeah,
to kids
yeah.
and things to do that.
Okay.
But other people, please linger here. You'll be here for a little while. We have a reception. We have 45 minutes or so for people to interrogate you. So thank you so much.
Amazing. Thank you.